questions to get them answered on my next live show. Welcome, guys. So happy you can be here. I already see several people in the chat. If you're here, make it known. Let me know that you're here. Say hello in the chat. I see Ibrahim. I see Vault Boy. I see Azu. I see Krista. I see Jessica. Thank you guys for being here. I'm excited to share all of the different topics that I'm actually going to cover today. And it's a good amount of topics. 3 main topics is what I'm going over today. And I'm excited about it because this is literally $100 worth of tutoring that you guys are getting absolutely for free. And I just see another Jessica come in. Hello, welcome you guys. And more people, also April, not sure how to pronounce your name. K West. So welcome. So happy you guys are all here. By the way, so today I'm going to be going over heating curves. I'm going to be going over buffers, standard enthalpy of formation, so many awesome things. So if you're in the second half of chemistry or even the first half of chemistry or AP chemistry, all of these topics are for you. So happy you guys are here. I see Eduardo saying, hey. I see Gaming with Ryan saying, hi, Melissa, how are you? I'm doing well. I'm here. I'm happy to teach. I'm in my natural element, that's for sure. So I'm happy that you guys are all joining me today. And another thing that I wanted to mention, so if you guys are new to this live format and you haven't been to one of these live shows before, welcome. And how this works is you tweet your questions ahead of time at my Twitter, which is at HelloMelissaM, and use the hashtag AskMelissaMaribel. That just helps me see the comment or actually see the tweet. And then I decide at the latest on Friday and Saturday morning which questions I'm going to actually choose and create a lesson out of it. So I highly recommend, if you haven't gotten your questions answered just yet, or if you have other questions, definitely tweet me. I will be picking next week what I want to teach for the following Sunday. I highly recommend it. By the way, as a hint, the earlier you tweet throughout the week, the most likely I'm probably going to pick it. Okay. So I highly recommend tweeting me earlier in the week rather than like the day of. My lesson will already be done by then. Okay, and for everyone else who has other additional questions, since I am going over 3 different things, heating curves, buffers, and standard enthalpies of formation, and if you have a different question on it, I highly recommend checking out the description box. I have several resources there. So at the bottom of the description box, what you're going to find are like links to online tutors, another link to something that I personally recommend. It's called Chegg Study. It's pretty much like homework help. So it really was helpful to me throughout all of my science classes. If you guys didn't know, I was a chemistry major, so that means I took a ridiculous amount of science classes and math classes. So Chegg Study was a great way to just help me understand my homework and actually understand the lessons in general. So I highly recommend checking it out. I couldn't afford a tutor at the time, so I understand what it's like to be not being able to afford a tutor or the resources that you need for school. So I saw that Chegg Study was a lot more affordable than actually having your tutor, and it did the job. So that personally, I highly recommend checking it out. Okay, all those links will be in the description box of this video. And then, of course, feel free to ask me questions on today's different topics, which, as you see on the screen, are those main 3. So let's jump right in and start talking about heating curves. Okay, so heating curves. What we're going to end up seeing with heating curves, and some people tend to confuse it with like phase diagrams, they're a little bit different. Phase diagrams are still talking about how we're changing from like a liquid to a gas or a solid to a liquid and so on. Heating curves are essentially talking about how much heat is being absorbed or how much heat is being released. And I want you to think of it this way. If we were to have some sort of ice cube, right? So if I were to place, let's say, an ice cube on my hand, right? So if I have an ice cube on my hand, essentially what's happening is the ice cube is melting because my hand is warm, right? So what's happening is that ice cube is going to melt, and I want to know how much of that ice cube is actually, like, how much heat is that being absorbed? Because the ice cube is absorbing the heat of my hand, right? That's why it's melting. So essentially, that's kind of the idea that we're doing here, is we're seeing how much heat is needed or will be absorbed when we go from, let's say, an ice cube to a gas, okay? So like vapor. So a lot of these questions are going to be kind of looking at that, and that's what I want you to think of. It's how much heat is it going to take to go from like a solid to a liquid, or even from a solid to a gas. And I'll show you the process throughout. So this heating curve is a really common one that you're going to see. It's specifically of water, but I'm just going to give the generic sort of case right now. So I'll start building this. So the first little line here, the vertical line here, is going to talk about a solid. And then let's say we have a horizontal line now. This is talking about the process of going from a solid to a liquid, which is known as fusion. Okay, so essentially, actually, let me bring back my liquid. Okay, so essentially what's happening with fusion is it's literally the process of, okay, we're not exactly at a liquid just yet, but there has to be that like middle portion where the solid is becoming a liquid, right? And that's what fusion is talking about. It's that middle portion where the solid isn't quite a liquid just yet, but it's getting there, right? So that's fusion. And then next, this vertical line, again, we have a liquid. Next, this other portion, the horizontal portion, is going to talk about how the liquid isn't a gas just yet, or it's not a vapor just yet. So it's that in-between phrase once again, or it's the process of a liquid becoming a gas, and that's vaporization. And then lastly, that vertical line again just goes to a gas. That's as far as we can go. There's nothing else that we can, go past a gas when we change it from a liquid form. So this is essentially the main processes that we're going to be looking at for heating curves. There are specific formulas that relate to each one of these. And you might have seen this already. This is part of thermochemistry and calorimetry. So all this is saying is we're going to see this formula. Okay, Q equals MCAT. It's just a nice way of remembering it. Kind of like if you want to be a doctor, you'll have to take the MCAT, but it just literally looks like it says it's the MCAT, right? So it kind of looks like an A. Just a way to remember it. Now, you'll notice that the solid, the liquid, and the gas will all have the same formula. All right, so that's always the case. And it's always going to be, little hint for you, it's always going to be the vertical. All right, the vertical lines will always be that change in state. All right, so that's how I know, okay, instantly it has to be that Q equals MCAT for each single state, the solid, liquid, and gas. Where it's going to change is fusion and vaporization. We're going to see a little bit of a slight change in our formula. So we will have N, and actually, let me talk about what N is. So we'll have N, which is actually equal to moles. There we go. I knew I had it. There we go. So this is our formula for fusion, where N just means moles. And then for our solid, M means grams or some sort of mass. And by the way, it will be in grams. So that's something to know. And let me actually go over that formula real quick, just in case you guys need a refresher on calorimetry. So M just means mass, that's measured in grams. C means the specific heat capacity, which is measured in joules per grams per Celsius, or divided by Celsius, okay? And then that's what C is. And then RT, that little triangle or delta just means change. So change in temperature, meaning the final temperature minus the initial temperature, all right? So that's essentially what we have for that formula. Now for our fusion formula, Q, or Q, meaning heat, is equal to N, which is our moles, and this just means the change in enthalpy of our fusion. So enthalpy of fusion. So, and by the way, I'm just gonna keep throwing out what everything means. So H, or delta H, just means it's a change in enthalpy. Enthalpy is a fancy word for heat transfer. Okay, just means we're transferring heat, and we're seeing how much heat is being either absorbed or released. And then for vaporization, it's really similar. So we will have N again, and that's our moles. And then we'll have, instead of fusion, it will be the enthalpy change of our vaporization. These are extremely important for you to know. So make sure you know this type of heating curve. Now we're going to keep going, and there's a little bit more to it as well, where you're going to have to build something like this, draw a heating curve and understand where all the different parts are, and seeing how far are we melting the ice to all the way to a gas? Are we melting the ice all the way just to a liquid? And finding out how much heat in total will it take, or will be absorbed or either released. So something to note is this first little corner is our melting point. Okay, so this is going to talk about it being our melting point, and then this little corner up here is either going to be the boiling point or where we stop. And I'll give you an example after this. But this is essentially what we're talking about, all right? So this little corner here is the melting point. This next corner is our boiling point. something to know, and I do expect you to know this, by the way, most professors do as well, is the heating curve of water. Knowing when the melting point of water is, that is 0 degrees Celsius. And for our boiling point, that's 100 degrees Celsius. Make sure to know that, all right? So a lot of times questions, like different professors and teachers just ask this type of question and they don't tell you what the melting point or the boiling point of water is. They expect you to know it. At least that's what I had in my case. And for a lot of my students, I saw that too. So make sure to be aware of that, all right? So just know the melting point of water is 0 degrees Celsius, boiling point is 100 degrees Celsius. Okay, so what we're going to do, let's actually do one of these, all right, now that we're seeing this. And actually, before I even move on, I'll get back to it because I want to teach you guys how to do it. Okay, let's apply this. It'll make so much more sense once we're actually like building this all out. So let's say we had a question and it said how much heat, and let's follow along. So how much heat in joules, and remember heat just means Q, right? Heat just means Q. In joules is required to convert 10 grams of ice, and we know ice must be a solid, right? So our ice is a solid. And then gives us our first temperature at negative 10 degrees Celsius to water. So water, we know that's in its liquid form. So I'm just going to put an L, just meaning liquid. And then at 50 degrees Celsius. Okay, so what am I given altogether? Well, I'm looking for Q in joules. And then I'm also given the mass of my overall solid. So I know my mass. Okay, cool. So I know my mass is M is equal to 10 grams. I know that my first temperature, so I'm just going to say that this is T initial, so little I. And then our final temperature, so T final. Okay, so what I want to do first is just see how far up that little ladder, that little heating curve, we're actually going to go up to. So a lot of times they might even give you, and by the way, they provided us with like the specific heat capacity of ice, of water, the enthalpy change of fusion. A lot of times what you might see on an exam or even on a homework question is they'll give you too much information. Okay. And they're trying to do that on purpose. Unfortunately, they're trying to kind of test your understanding of it, or how I sometimes say it, they're trying to trick you. So beware of this, okay? So what I want you guys to see is first start off with identifying how far up that little ladder am I going to? Am I going from a solid to a gas, or am I going from just a solid to a liquid and stopping there? Because in that case, you wouldn't need vaporization, right? You wouldn't need every single little part of that ladder or little heating curve that I was talking about before. So let's draw this. What we would start with is a solid because we stated, okay, it's at an ice, right? It's an ice right now that's in its solid state. And then it's going to water, so I know that has to be a liquid. So these are the formulas that we're going to see. And I know this, by the way, so once again, I figured this out because it just told me of an ice to water. That was the hint right there. Ice is our solid. We're going up until to water, which is a liquid. So these are the three different things that we're going to look at. These are the three different formulas that essentially we're going to solve and then add all together. Because this is asking for how much heat, but really it's saying how much total, like in total, how much heat do we need to go from this solid to that liquid? So we're going to see this in here. So we're going to see every single one of these formulas. Next, I'm going to start writing all the different temperatures that we were given. So our initial temperature, I'm just going to place down here, which was that negative 10 degrees Celsius. The final temperature, because that's where the water or the liquid is at, is 50 degrees Celsius. So I'm going to place that up here. And then next, on the middle portion right here, remember, this was our melting point. So we're still talking about water, so we know the melting point of water is 0 degrees Celsius. That is extremely important information to know. If you were to just have, let's say, found the change in temperature and subtracted 50 minus a negative 10, that would have completely given you the wrong answer. So that's why I highly recommend you guys know the melting point and the boiling point of water, because this also tells us that, remember, the melting point of water is 100 degrees Celsius and we stop at 50. So that means it never makes it to a vapor, right? It never reaches vaporization. So that's how we know to stop, and we don't include that in our formulas. Okay, so what we're going to do is we're going to find every single one of these, every single little portions of these. And then at the end, so meaning I'm going to find how much heat is needed for a solid, how much heat is needed for this fusion, for the liquid, and at the end we'll add every single one of these together and that'll be our final answer. So let's do that. Okay, so I'm going to start off with a solid, just plugging everything into Q equals MCAT. And then what we're going to see is our mass isn't going to change, right? We have 10 grams of ice, so that's going to be right here, 10 grams with our M. Our specific heat capacity of the ice was given, so that was at 2.108. And then we want to plug in our final minus our initial temperature. So our initial temperature was right here, right? We're just looking at this solid portion. So final minus initial would actually be 0 minus a negative 10. So that's what we would have here. And that's what we see here, right? 0 minus a negative 10, really it's plus. So we're going to see that that's a positive 10, multiply straight across. And then we're going to see we get our joules because our grams would cancel, Celsius and Celsius would cancel, leaving us with joules, which is what we wanted. So that's just the heat specifically for our solid. Now let's do the next part. Let's figure out however much heat we have for our fusion or part 2. So we're looking at fusion. We're going to plug everything into this formula. And then the first things first is we need to convert grams to moles because that formula, remember that N is measured in moles. So I'm going to start off with 10 grams of ice, and then I'm going to multiply this. So I'm going to multiply this by, really divide this by the molar mass of water. So that's what that 18.02 is. It's just the molar mass of water. And then from here, these grams and grams would cancel, giving us the moles of water, which is what we wanted. Next, I'm just going to plug this into the formula. So plugging everything into the formula, they gave us our enthalpy change of fusion, which is exactly what I plugged in, right? That's our formula. So then I'll multiply straight across. Our moles would then cancel. Moles and moles cancel, and we have our kilojoules, which we'll later have to convert to joules. But for now, that's at least the second part. So, okay, so right now it's really just plugging into the formulas. And then lastly, for this next part, we're going to see the liquid. And it's still that Q equals MCAT. So I'll plug in 10 grams of ice because that's still the case. And then we also have our specific heat capacity of water, which is given. Now, a little note as well, you're not always going to be given the heat capacity of water. At least that's, like I said, these are just different things that I've seen professors do. It could be different in your case. I highly recommend asking your professor if you're not sure that if they're going to provide you with the constant or a formula, but it's better to be safe than sorry. So I do recommend knowing also the specific heat capacity of water because that is something that I've just seen and you are going to need it. So that 4.184 joules per gram Celsius is something you will definitely need. So that's what I plugged in here. That's the specific heat capacity of water in its liquid form. And then once again, I'm going to plug in our T final and our T initial. So our final temperature, because we're going to a liquid, is going to be here at the 50. Our initial temperature isn't that negative 10, it's actually 0 because we're just looking at where did we leave off, right? We left off on fusion, which is right here, and we're just focusing on that vertical portion of our liquid. So our initial temperature would have actually been 0 and our final temperature would have been 50. So I'll plug that in. So final minus initial, which would be that 50 minus 0, and which is really just 50. Then from there, we'll multiply straight across, and then that would give us our joules. So we found every single one of our heats or joules of every single one of these little portions of the solid of the process between, solid and a liquid, which is fusion and liquid. The next thing is we need to make sure that all of these units are the same to be able to add them together. So our joules, I'm just going to convert this to joules because that's what they wanted, right? The initial question said they want heat in joules. So I'll convert the kilojoules to joules. And then all I have to do is multiply by 1,000, which is 1,000 joules is equal to 1 kilojoule. So doing that, I get this value. Last step is just to add everything together. So add everything together, and this would be our final answer for our overall heat that is absorbed. So that's the general process of these types of questions. They may seem a little bit longer just because we have so many different formulas, but my main thing that I want to recommend to you guys, let me go back to the heating curve. What I want to recommend to you guys is just draw this out. Literally see how far are we going up this little kind of curve or I think of it as a ladder. How far are we going up? Because you're like in our previous case, we didn't need vaporization or gas. We just went from a solid to a liquid and that's it. And of course we required fusion, but we just had 3 different formulas. We didn't have all of these. So another little note is what if we weren't going in that direction? Meaning, what if we weren't going from a solid liquid then to a gas? What if instead we were going backwards? If we were going from a gas to a liquid or a gas to a solid or a liquid to a solid? All right, so if we were going the opposite way, what would happen is it would actually be negative. So our formula changes just slightly, where all of these now have a negative in front of, like, this has a negative in front of the N, this has a negative in front of the M. So, and let me just make this really clear. So something like that, all right? So all of these now are going to have a negative in front, just because we're going the opposite direction, because we're going from a gas to a liquid or a liquid to a solid and so on. So that's the only difference when we're going the opposite way. So beware of that, all right? So that was heating curves. I hope that's making some more sense. Let's see how everyone's doing. Cool. So let's keep going. And if you are liking this live show, if this tutoring session is helping you out, make sure to give this video a like. I always like to see your feedback and see how many people I can help out. So let me go to the next part, which is going to be buffers. So buffers, come on. Buffers is the second part. It's part of AP Chemistry, and it's also part of the second half of General Chemistry. So that's what I'm going to talk about right now. Come on, there we go. Okay, so let's just discuss what in the world a buffer even is. So a buffer, I'm going to talk about kind of the more chemistry way, and then I'm going to give you an example that we can all relate to. Okay, so buffers. Essentially what a buffer is, it's going to be some sort of mixture of a weak acid and a conjugate base, okay? So knowing something like that is going to be very helpful. And by the way, that's always going to be the case. There's going to be specific formulas that we're going to look at later, but that's something that I just want you to instantly know. Nothing's really going to be strong, right? Buffers are relating more to something that is a weak acid and a conjugate base. Those two combined will then form a buffer. Now, essentially what buffers are doing, they resist pH change. So what I want you to think of it as is our blood is actually a buffer. And I'm going to give kind of a little bit of an extreme example, but think of it this way. So if I were to take a drink of coffee or orange juice, something that's really, really acidic, then essentially what would happen is if my blood wasn't a buffer, then that wouldn't be so good, right? My body wouldn't be able to adjust to the acidity. And that's because our pH is so low, right? If it's acidic, that means our pH is below 7. And something like coffee or something like orange juice, I believe, has a pH that's rather low. I want to say 4, but I'm not too sure. But I know it's low. So the nice thing, and the fact that our body can take so many cups of caffeine or coffee in general, is because our blood is able to neutralize it. And that's the general concept with buffers is let's say if I were to add something acidic, right? The conjugate base part of that buffer is able to neutralize it and not let my blood change its pH and become too acidic. All right, so it's still like regulated. And then let's say a different case where I were to drink something that's rather basic, like milk. If I were to have a glass of milk, which is more basic, then what happens in my blood is the weak acid, which is part of the buffer, that's going to neutralize the basic milk or whatever substance that I would, consume. So that's essentially the concept there, is that blood or that buffer per se is going to resist or help like neutralize, so there isn't a major pH change no matter what I'm adding. Okay, so that's essentially the concept here. What makes a good buffer, now I'm going back to the chemistry side, What makes it a good buffer is the ratio between our amount of concentrations of conjugate base and our weak acid. So I want you to think of it this way. When I'm talking about ratios, I'm really talking about fractions. Okay, so looking at something like this, on the bottom here, we see our conjugate base is on top, and that's divided by our concentration of weak acid. Remember, these brackets just mean concentration. So if these two are the same, so if they're the same concentration, like let's say if they're 0.1 and both of these are 0.1, if we divide that, it just gives us 1. Or if we were really, really close, and let's say we had something that was 0.1 and the other one was 0.101, even if it was just really close and not perfect, as long as it's generally close to 1, that ratio, when we divide those two together, then that tells us it's a good buffer. Okay, we want it to be as close to 1 as possible. So I've seen that as a general question before on like multiple choice question. I see it all the time, is which one would make a good buffer? Well, doing this ratio is going to help you figure that out. So if it's a conjugate base, first things first. I remember this trick question that I saw a while back, but it was giving you two different, an acid and a base, and it was asking which one is a good buffer. And it wasn't even a buffer. So make sure to double check that, okay, this is my weak acid and this is the conjugate base of that weak acid. It's not just on its own, okay? So that's something that I kind of want you to make sure. Make sure, one, it's weak acid, and make sure its conjugate base is actually there when you're asked that question. And then next, the other way to figure out is it a good buffer is literally dividing those two together. So if they gave you your concentration of your conjugate base and the weak acid, divide them. The closer it is to 1, the better the buffer. Okay, those are my little tricks for you for multiple choice questions. Okay, let's do one. So this is going to be more of the free response, which is the main chunk of your test. So if we were given something like this, where it says a buffer solution is prepared by adding 0.10 liters of a 2 milliliter solution of acetic acid to 0.10 liters of a 1 molar solution of base, NaOH. Okay, so, and we have to figure out what our pH of the buffer is. And of course, they're going to give us our Ka. So the fact that they give us our Ka tells us, well, yes, it has to be a weak acid, right? Because acetic acid, if you guys aren't sure, is a weak acid. So a little note, by the way, if you guys are not familiar to which one is a weak acid, what's a weak base, what's a strong base, and so on, I highly recommend checking out the description box. I do have in the very beginning area, I have a formula sheet, so it's a chemistry survival guide. I highly recommend downloading it. It is completely free, so make sure to check that out because I have a whole list of the weak acids, of the strong acids, strong bases, and so on. So those are ones that you will for sure have to know, like acetic acid is there, and you will also have to know the formula of acetic acid and the fact that it's weak. So that is I'll put a link, by the way, right now. I just put it in the chat. And then you'll see that in the description box as well. And then as we're going along with all this, by the way, I do have so many formulas that I will be using. So all the formulas that I'm picking from are also going to be found in that. It's a chemistry survival guide. It's really just a whole formula sheet, right? Different tables, different things that I know actually you guys will benefit from having all in one place. So make sure to check that out. And one other little thing, if you're struggling with your homework, if you're struggling just overall, make sure to double check that all the different resources actually that I hand selected for you guys in the description box. Towards the bottom, you'll be able to find, let's say if you need an online tutor, I have links to that. If you need homework help, which is something that I definitely needed when I was in college and that I used, it was called Chegg Study. I personally used that all throughout college for my physics classes, all my biology, chemistry, math classes, all of my STEM classes that I had to take. I definitely benefited from using Chegg Study. It was just a great way to see step-by-step solutions of different questions that you may have. All right, so let's say there's like a homework question that you have just tried so long for and you're frustrated, and I completely understand that. That was a great way to just relieve that frustration and see all the different steps to see where I was going wrong and what I was missing. So make sure to check that out. It will be in the description box. And as a little disclaimer, by the way, I am part of their affiliate program. So if you do decide to purchase Chegg Study, I do get a small commission. All that goes to is making more videos for my channel and other resources for you guys. So just wanted to mention that. Okay, so acetic acid, what is it? Let's figure that out first. First things first that I want you guys to look at these types of questions is they're not going to provide you with the balance equation most likely. So you're going to need to figure that out. So let's do that. So let's say we had to know, one, that this is acetic acid, right? So acetic, meaning it's acetate. So acetate is just that C2H3O2, and it has a -1 charge. And then the fact that it's an acid means there is a hydrogen in front. So that's how I knew that this is acetic acid. Next, it's telling us that we are adding acetic acid plus our NaOH, which is a base. So anything ending in OH is a base. It's a common base. It's actually most likely a strong base. So which NaOH is, it is a strong base. So those are the two that we're going to add together. And essentially what's going to happen is we're going to form our conjugate acid and our conjugate base. And what I want you to think of when this is all happening, an acid is going to donate its hydrogen, or we call it a proton. Proton meaning it has a positive charge, right? H plus is a proton. So what would happen is this H is going to donate its hydrogen, and what would combine and what would be left over are Na and our acetate. Those would form one, and then that H and OH would form water. So that's essentially what's happening. And another thing, by the way, what you're going to see possibly in class or even later in this question is we don't even care about Na. And the reason why we don't necessarily look at sodium too much is it will dissociate. It's not really part of this process. And dissociation, remember when I mean dissociate, it just means breaks apart or dissolves essentially. And it breaks apart into its separate ions. So I don't really necessarily care too much of Na, and you're going to see that later on or in class. So if you have seen some of these questions where you're not including the Na, it's not wrong. It's really just focusing on the major process as to what's happening. So like you might have seen this as, let me write this, as OH minus, and then this is going to form C2H3O2 minus. Why is it minus? Because we lost a hydrogen. And remember, acetate in its polyatomic ion form is going to have a -1 charge, and that's why I have that here. And then when we're adding that H and that OH, we're actually neutralizing this, and that's why we're going to get a neutral compound, or actually molecule, which is H2O. All right, so that's something to definitely know. All right, so let's continue with this now that we have our balanced equation. From here, let's just calculate the overall pH of the buffer and see what we need to do. So with these types of questions, what we want to do, because they're giving us the amount of liters and the molarity, same thing here, we need to figure out how many moles we have for each. So we're going to figure out the amount of moles we have of our acid and the amount of moles that we have of our base. And remember, our acid in this case is that acetic acid, and our base is going to be that NaOH. So let's just start off with figuring out how many moles of acid we have. I'm going to start off with what they're giving me here, which is 0.10 liters. And that's what I'll see. So we're going to start off with that 0.10 liters. And what I want to do, remember that molarity can be used as a conversion factor. All that means is I can separate molarity, so capital M, molarity can be separated to be moles divided by liters, which is exactly what I'm doing here. This 2 or whatever number goes with the moles, and it's per every 1 liter, which is exactly what I'm showing here. All right, so this is just 2 moles of acetic acid per every 1 liter. This is essentially the molarity. We'll multiply straight across, and that's what I get for my acid. So these are my moles of acid. I'm going to do the exact same thing to find the moles of our base. So same concept where we're going to have here, it tells us 0.10 liters of 1 molar solution of NaOH. So those liters would cancel, and we only have 1 mole, so this is going to be our moles of our base. So it is really important for these types of buffers, these types of questions, because they give us our amount of liters and the concentration. That's our hint to know, all right, how many moles do I really have of my acid? How many moles of my base do I really have? And that's going to be like our second step after finding the balanced equation. All right, so the next thing, The reason why we found the moles is because we want to form something called a BCA table. All this means, BCA table just means before, change, and after. And what in the world is that? So what that's telling us is, one, it's a little bit different from an ice table. So an ice table handles everything in its concentration or in molarity. But a BCA table is going to be in moles. All right, so that's the main thing to figure out which one's which. So a BCA table is going to be with moles, and an ice table will be used for molarity or with molarity. And you're going to typically see that in titrations or chemical equilibrium. And then for BCA, you're typically going to see that with buffers. All right, so definitely know that. But it works the same sort of way as an ice table. Main difference is just the fact that we do know what our X value is, and we know that it's in moles. So I'm just going to start off with the amount of moles that I found in the previous step. All right, so this is what we found previously, the 0.20 moles of our acid and the 0.10 moles of our base. We have no clue what our product would be because we haven't formed anything yet, right? We haven't done everything yet. Now, do we know what our change is? Yes, we do. So the reason why we know what our change is because we are adding base to that buffer solution, all right? So since we're adding base, that's going to be our change. And then another thing, by the way, is the fact that we're actually adding a strong base. And that goes back to the list that I was talking about, where NaOH is a type of strong base, while acetic acid is our weaker acid. So in this case, I know that my base, because it's stronger, is going to change this altogether. So that's why I'm subtracting the same amount of moles that I found for our base from our acid and from our base. All right, so that's going to be something to note. And then, by the way, you're always going to subtract on the reactant side because you're using that up. And then on the product side, we're going to add because it's being produced. So in this case, I really am just going to combine these two together. So really just combining those two together. So think of it like you're just adding straight on down and just adding. And then the A is going to be the after you actually add those two together, you'll get these values. So you're going to get 0.20 minus 0.10, 0.10. This is going to subtract and just be 0. And then the next one's going to be 0.10. Why do we care about this? So why is this important? The reason why this is important is because we need to know what our, and actually I'm even going to go back for a second. Think back to what a buffer is, right? So we said a buffer was a weak acid and its conjugate base. So we need to figure out our concentration of exactly that. We need our concentration of our weak acid and our conjugate base because that's what makes a buffer. So in this case, what I'm doing is I'm just seeing how many moles do I have right now after adding that strong base. How many moles do I have left in that buffer solution? So, and specifically, I'm looking for the moles of our weak acid and our conjugate base. And then how do I know that that's our weak acid and conjugate base? Well, this for sure we said was our weak acid, right? Acetic acid. A conjugate base is going to lose a hydrogen, all right? And this is exactly that. This loses a hydrogen, right? We said that we don't necessarily care about the Na, but that is what we're going to see for our conjugate base. Okay, so this is going to be the amount of moles for our weak acid. This is the amount of moles for our conjugate base. And then from here, what I want to do is figure out the molarity of each. So what I'm going to have to figure out, because we have the moles, remember molarity is measured in moles divided by liters, and the specific liters that we will see is the total volume that we had initially. So what we added, remember in our initial question, was 0.10 liters of acid and the same amount for our base. Adding those two together will give us our total volume. So then what I have to do now is just divide the amount of moles of our weak acid by that total volume, and that gives us our concentration or our molarity of that weak acid. We'll do the same exact thing for our conjugate base, and this is going to be really helpful because there's a specific formula that we will use, and we'll do that now. So these two are extremely important to know or to be able to figure out. And then what I want us to do now is to just find the pKa. Finding the pKa is this formula. So pKa is equal to the negative log of our Ka. Remember, our Ka was provided. It was given to us. So all I have to do is plug that in. So I'll plug in my Ka value. And then when I plug this into the calculator, That gives us a pKa of 4.77. Next up, this is the formula that we're going to use to be able to figure out our pH. So this formula is the main formula that you're going to see for buffers. So make sure to definitely know how to use this formula. And by the way, what always goes on top is that conjugate base, and what goes on the bottom is our weak acid. And I mean the concentration of it. So that's why that was the whole point of this, was to figure out what is the concentration of our weak acid and our conjugate base to be able to then plug this into the formula, and then it gives us our pH, which is what we're asked to find. So now we have everything. I'm just going to plug that all in. And then remember what makes a good buffer. So the fact that these two are literally the same value, that's going to cancel out and just give us log of 1. Log of 1 is 0. So then that's why we get the exact same thing as our pKa, which is 4.77, and that would be the case in this case. All right, so that's just the first part. I'm going to keep going. There's a part B to this question. So that was just the part where they're asking you to find the overall pH of the buffer. Now let's see something a little bit different. If we were to, let's see what they're asking now, actually. So now part B is saying 0.10 liters of our HCl. So now we're adding acid instead of base. So we're adding an additional amount of acid to this amount of volume of our buffer solution that we found previously. And they're asking us what is the pH of the resulting solution. Okay, so what we're going to have to do now is figure out the amount of moles, right? We still don't know how many moles of acid we now have. So that's going to be important to know. We need to figure out how many moles of acid we have, as well as how much of our moles of our conjugate base we will see. And it's just because this is our acid, this is most likely we're still going to need the conjugate base. So, and that's kind of just what we're going to figure out, just like we were doing previously. So this is a tiny bit different, where I wrote it a little bit differently, and this could have also been HCl, by the way. Remember that HCl is a type of strong acid, all right? And once again, that's part of the list. So HCl is a strong acid. All that's really talking about is that's going to be our concentration of acid in the solution. Whenever you're given H3O plus, which is known as hydronium, it's a hydronium ion, ion just meaning it has a charge. So whenever we see that, that's essentially just telling us that it's talking about an acid. It's talking about the acid concentration. All right. So that's why instead of placing HCl, I just placed acid in general. I put the H3O plus instead of that. And that's okay to do. I actually recommend doing that instead. And the reason why is because this is now gonna relate to our conjugate base. And this relates to our conjugate base now, right? Because we're adding acid. And then I'm going to actually go back for a second because I want to make sure that that is clear. All right. So the reason why I'm now switching the formulas is because in part A, we were adding a base, right? And then think of it this way. Remember that idea that I was saying, if I were to drink something that were acidic, then the conjugate base would neutralize that, right? Or if I were to drink something that was basic, like let's say milk, then the buffer in my blood, the portion of it, if I were to drink something that was basic, then the acid portion would then neutralize that. That's exactly what we're seeing here. So what we're seeing here is that if I were to add base, NaOH, the weak acid has to combine with it, right, to neutralize it. Now, and that's why we have this sort of this balanced equation. That's how I knew to just instantly write that. And then now with part B, let me get there. Now with part B, come on. There we go. So now with part B, what I'm seeing is since we're adding acid, a strong acid, then the conjugate base will neutralize that. And that's why it's switched. All right, so now we see the weak acid is on the opposite side. So that's going to be the case whenever we're kind of changing this up, and how you exactly, how to write the overall balanced equation is dependent on whatever you're adding. So if you're adding an acid, it will combine with the conjugate base. If you're adding a base like NaOH, it will combine with the weak acid. All right, so that's how I knew. So then, okay, this works out perfectly, because if this is our acid, remember that an acid is going to donate a hydrogen or a proton to the base, because this is our base. Another little note, by the way, acids tend to have, if they do have charges, acids have a positive charge, bases have a negative charge. So now I would donate this hydrogen here, and that's exactly why we have our weak acid now, or our conjugate acid. And then next, I would see, okay, well, I gave up a hydrogen here. That's why I have one less hydrogen to make water. So that's going to be our balanced equation. All right, next step is we want to figure out how many moles of our acid we have. So we're going to do the same sort of process again, where I'm going to take the 0.10 liters and I'm going to multiply that by the molarity of our strong acid. So that would have been 0.20 moles per every 1 liter, multiply straight across. That gives us this for our conjugate, for our moles of our acid. And then next I'll find the moles of our conjugate base, or our base in general. And I see that we started off with 0.40 liters. All right, so we started off with 0.40 liters. And remember that we found the concentration of our buffer in part A. So in part A, we literally found that the concentration of our buffer for both of them, right, was 0.50 molarity. So a molar solution of 0.50. So that's how I knew instantly to just like what to use, what to multiply by, because we found that in part A, which was needed. So then I'll multiply those straight across, and this is what our moles, that's how much we would have. Next step is to, once again, figure out what the change is, all right? So let's figure out what the change would be after adding the acid. So that's going to be our change. The fact that we added acid is going to be the thing that's literally changing our buffer solution. So I'm going to start off with just the moles that we found in part B in the previous part. So those are the moles that we just found. And then we also knew that there was 0.20 moles of our weak acid. The reason is because that's still part of that's still part of the buffer solution, right? Buffer solution is a weak acid and its conjugate base. So then that's how I know that those two are the same. And then this is just what we found for our concentration of our acid, our moles, of our acid. So then next I'm going to subtract that here because that's what's changing, right? I'm adding acid, so that's the change here. So subtracting those two and then adding on the product side because we always add on the product side. And then we're just going to combine, so just combining every single one of these, right? We're just combining. And then this is what we would get for that part. So then now I'm just going to see how much do I have, how many moles do I have of that conjugate base and its weak acid. And this is what we would see. Next step is to convert this to change this to molarity. So we'll divide by the total volume. And then just looking at this, remember, and actually here. So I'm just going to add everything together. And then where I found this was in the question in part B. So we had 0.10 liters plus 0.40 liters. That's what I'm combining right now. And that's going to give me the overall total volume, which would be 0.50 liters, okay? And then next, I'm literally just going to do what I did before. So what I did before was just I found the moles. I'm going to divide that by the total volume. And now this gives us the concentration of our conjugate base. And then next, I'm going to find the concentration of our weak acid. And that would give us that. From there, we're going to use the same formula that we found before. So we said our pKa, that doesn't change, right? That's going to be the 4.77 because we still have the same Ka for acetic acid. So we're going to find the pH using the same formula. We know that our conjugate, right, A minus just means that's going to be our conjugate base, and then this is going to be our weak acid. So I'm just going to plug everything in because that's what we found prior. And then now when doing this, plugging this into my calculator, by the way, what you should do first in your calculator, divide these two, then take the log of it, then add 4.77, and that's going to reduce this a little bit. It's going to be 4.68. So that's actually how you know it's a good buffer. The fact that it's only a slight change in the pH. It like resists that pH change. So that's something to also kind of see. And why did it go down? Well, because we added acid, right? We added some HCl, which is a strong acid. Because we did that, that moves the pH a little bit down to be a little bit more acidic. So it doesn't move it too far, but it does move it a tiny, tiny bit. Okay. So now let's move on and do a question on standard enthalpy of formation. So I feel like the formula may look intimidating, or just the question itself might look like, what in the world am I doing here? But it's actually just plugging everything into the formula and doing math and you're done. Okay, so I'm going to show you how simple this really can be and how these are like free points to you on an exam. So let's say if we were given this type of question and we were asked to find the overall change in enthalpy of our reaction. By the way, I'm just going to mention real quick that like what all these symbols mean, because we are going to see this a lot, and you're going to see this in the second half of chemistry. The second half of chemistry will have a lot of different symbols that you are required to know. So, and this actually does come back in the second half of chemistry. So remember that this triangle, or we call it delta, and it shouldn't have a little tail there. There we go. So this just means change. So meaning we're changing it up, either going from final minus initial or so on. And then this just means enthalpy. So remember, enthalpy is heat transfer. That RXN just means of the reaction. Okay, just means reaction. And then this little circle here, or degree symbol, is just talking about it being in its standard conditions or in its standard form. So standard conditions essentially is saying there's a specific temperature, 25 degrees Celsius or 298 Kelvin, and a pressure of 1 atmosphere. So those are the conditions that it's saying. It's saying that this gas or this reaction is held at that specific standard conditions of 25 degrees Celsius and 1 atmosphere for our pressure. That's all it says. Okay, that's all it means. So just a little side note, because you will see this all throughout, actually, the second half of chemistry. Okay, so the formula, let's bring in what our formula is. And by the way, they will provide you with a list of your standard enthalpies of formation. If they don't, it will be in the back of your book. So definitely make sure to know where that is or to find that, or even ask your professor, are you going to provide this to me? Because they have to, okay? So, and if you don't see it, raise your hand, ask them. Sometimes they forget, but that's just something to note. This is the formula that you're going to use and you're going to see, and it's going to be so simple, all right, to just plug everything in, and it makes life easier if we know what everything means. So essentially, this N is just going to talk about the moles. And by moles, I'm really just talking about these coefficients in front of that specific molecule. So now what we're going to see, and what this summation notation means, it just means we're going to add the amounts of our products. All right, so this is really talking about the sum of our products and the sum of our reactants. We're going to then subtract those two from each other. So that's exactly what I'm going to do. I'm just going to plug everything in. Okay, so just highlighting what we need. Remember, these are our reactants, these are our products. So we start with the products because that's what's part of our formula. And we're going to need to put the amount of moles we have of that specific product in front and multiply by the value. So this is the formula that I'm going to use. And how I figured this out was just the fact that our first product, right, the first product here is CO2. So that's what I put here, CO2. And then next, I have to place the N, or the amount of moles, in front. So 4 goes in front. Next, we have our water. That's our second product, right? So that's going to be H2O and a 2 in front. Subtracted by, and remember, these are added together. That's what this sum means, or summation notation means. And then next, or sigma, that's what I was thinking. So C2H2, that's going to be our first reactant. So our first reactant, right, that we saw here, has to have that 2 in front because it's the amount of moles that we have. So that's here. And then same thing with our O2, that's our second product, our second reactant, that's going to be here. And I'm going to place an N, or the 5, which I see is in the balanced equation. So this is the general idea. The next thing is really just to plug in what we know we have for our standard enthalpies of formation. So they're going to have to give you this. And by the way, I know I realized I didn't place the states here, but on most charts, you will see the different types of states. Like, double check that it is water in its liquid state and not in its gas state, and so on, just because that it does have different numbers and you would get the answer wrong. So just make sure to be aware of that. Here I provided the correct values, so you don't have to worry about that. But just in case you see that on an exam or homework question, make sure it does have the proper state, the same one in the formula. So I'm just going to plug everything in. All right, so let me go to the next slide. This is what we saw before. This is what I just moved it over. So this is the same thing that I'm doing. All I'm going to plug in is literally all of the values that we see on the table for the proper one. Like, like for CO2, that tells us, okay, it's this value. It's negative 393.5. I just plug that in and I'm going to multiply that by 4. Same thing with water. Okay, that's going to be this value, right? That negative 285 found on the chart. Keep going. So 2 times our C2H2. Here, this is going to be 227.4, plugging that in. And then O2 is just going to be 0, so I'll plug that in as well, and we'll do the math. So I'll start off here, just multiplying the 4 times this value and then 2 times this value. All right. And then I'll do the same thing here, 2 times this value plus nothing, right? So this is what I would get. And then next, just going to combine these two. The fact that this is negative is just because this is negative, and which one wins here? This would have been a minus. So then I'll subtract those 2 values, and this is what I would get for my enthalpy change of the reaction, my standard enthalpy change of the reaction. All right, so that's essentially it. And it's going to be in kilojoules, by the way. That's just something to note. This is going to be, the fact that I know that this says per mole, the fact that we placed moles here would cancel that out. All right, so that's why our enthalpy change of the reaction will only be the unit of kilojoules instead of kilojoules per mole. So that's the main thing, and that's really it for standard enthalpies of formation. Knowing the formula, knowing how to plug everything in and use it is the biggest thing, and that's actually the main thing that I see students. And then the other thing that I see students might make a mistake on was just placing the wrong value, and instead of like using liquid for water, they use gas or something like that. You know, they use the wrong state, and that's just what I've seen, just little errors. But other than that, that's pretty much the main thing. And yeah, so I'm going to see, Abdul says, question on naming acids. I have actually a video that goes into really good detail on naming acids, which I will place in the live chat right now for you. It's really good video. So yeah, it highly recommend. Actually, yeah, watch that. It's gonna help you a lot. It actually has helped a lot of students already. So I'll place that in the chat right now for you. But overall, this is what we covered today. We covered heating curves, we covered buffers, we covered standard enthalpies of formation, a lot of great topics. So if you are taking the first half of chemistry, AP chemistry, chemistry 2, these are all going to relate to your class overall. So, or even just general high school chemistry, you will see heating curves, as well as, I believe, possibly standard enthalpies of formation, depending on where you are. So awesome. So what I also wanted to go over and just talk about real quick is everything that you guys have seen in this, and like all my slides or all of this lesson overall. A lot of these tables are going to be in the description already. So the free survival guide, I highly recommend checking that out. Another thing, by the way, I actually just finished a new notes. So new notes on thermochemistry, and it does have standard enthalpies of formation. There are several examples of that, as well as Hess's law, calorimetry, it's coffee cup calorimetry, all the different calorimetries. It also includes just different ways of, like, let's say, how to write or how to understand endothermic versus exothermic graphs and what you would need to know for an exam. So it took a while. It took a while because it's over 50 pages and since this, thermochemistry is such a big topic, I made sure to include as much as possible and several different examples that I have personally seen on exams. So let's say if if you're asked to find the mass, or you're asked to find the change in temperature, final temperature, specific heat capacity, I made sure to give an example of every single one of those and the steps of what you would need to do and the formulas that you need and just the keywords. So I highly recommend checking that out. You can shop the notes in the description box below. These are new, and I'm happy to finally have those done and complete for you guys. So if you guys like how I teach, it's literally the same thing there in my notes. Everything is step by step with several different examples, and it's quite visually pleasing, I would say. So awesome. So there's that. And then another thing in the description box, what you will also find at the bottom is even more resources. So if you need additional help on maybe a totally different topic that I didn't go over today, then I highly recommend checking out the description box if you need an online tutor, or if you just need help with your homework and figuring out what in the world your homework is trying to tell you, then I highly recommend checking out Chegg Study. That personally helped me a lot throughout college. I used that all throughout college, and it was a lifesaver. So if you feel like, you know what, I can't afford a tutor right now, but I needed a different affordable option, that's what I did, because I couldn't afford a tutor at the time back in college. So essentially, Chegg Study was honestly the best option for me at the time, and I still think it is a great option. So make sure to double check that. The link will be in the description box towards the bottom. And then also, if you guys want your questions answered for the next week, a chance for them to be answered, make sure to tweet me. Okay, so please tweet me in the beginning of the week rather than on Saturday or Sunday, because I already have planned and created my lesson, which takes several hours to make. So just to make sure that you guys can get your questions answered, make sure to tweet me throughout the week, but towards the beginning of the week. And then just, tweet me at Hello Melissa M. I put a link in the chat right now. And then use the hashtag of Ask Melissa Maribel. And I will then pick different ones to answer on the following live session. So awesome. Thank you so much for joining me, everyone that is here. And make sure to give this video a like if everything that we talked about was really beneficial and helpful. And if you guys are liking these lives, make sure to give this video a like. Awesome. And I'll see you guys in the next Sunday Live. See you guys.